Hello and welcome to my capstone project, Conservation Through Classification, a machine learning approach to identifying wildlife in camera trap images. So for this project, the problem I'm analyzing is leveraging advanced machine learning algorithms to classify wildlife images more accurately and efficiently than human efforts can achieve. So for this project, there will be machine learning algorithms used that are specially designed for image classification. We're using convolutional neural networks and vision transformers. Have to assign 8 different animal classes um, from images captured in different wildlife areas. The championship model will be able to accurately identify each animal species, and there will also be images that don't have animals in them, blank images. It will have to identify those as well as the 8th class. So this project came around because there's a huge issue going on with wildlife conservation efforts. So conservationists need to observe the wildlife populations without interfering with them themselves because animals are very sensitive. They have better senses than us, so they can detect when people are around, so they need to observe them from a distance without messing up or interfering with the environment. So camera traps are surveillance systems. They capture images of wildlife and they pretty much take a picture every time motion or heat is detected. And these are placed in populated areas to monitor the wildlife. And each camera can capture hundreds or thousands of images each day. So one camera can even generate 150,000 images per month. And this manual image labeling process, as you can tell, is very time consuming, it's very tedious, and it's just prone to human error. So it would be much better if we had an automated computer system to handle this process. Now, the data set description. So this data was collected by the Wild Chimpanzee Foundation and the Max Planck Institute for Evolutionary Anthropology, and it was captured in Tai National Park in the Ivory Coast, all in 2017. The data has been clean labeled and it contains 7 different animals: birds, civets, which is an animal kind of like similar to a raccoon or a cat, like combination, a duiker, which is a type of antelope, hogs, leopards, monkeys, rodents, or blank, meaning it does not have a animal in the image. Each record in the dataset is a JPEG file from the camera trap, and there's also 2 CSV files, train and test features, and these CSV files contain the image ID, the file path, and the image capture site. So the sites in the training and test data are actually different, and this is to ensure that the model built will perform well in new locations so that the model built will actually be a usable model. And the last file, the train labels, which is the actual labels, contains just the image ID and the appropriate label for that image. And there's an example of one of the images that's in the data set. You can see the camera trap captured a photo of a monkey in the bottom right corner. So this data set has training data, which has about 16,000 labeled images, and then testing data, which is 4,500 labeled images. And in this situation, the test data is not labeled. That's what's actually going to be used for the competition submission. So the model will label that and then send that to the competition to get actually scored and see how well the model does. So in order to actually test and evaluate our models, I have to break up that training data into a training and validation. So 70% of the label data will be used for the actual model training, 30% will be used for the validation. And once I get the championship model, then it'll be used on the test set, which will be labeled and submitted for scoring. And you can see the counts of each image class below. So the target class imbalance. For my first visualization, you'll see right here that there is an imbalance in the target class. Hogs and birds have significantly less samples than other classes. You see, especially the hog class is very underrepresented. Um, so in order to handle that, when I was creating that training and validation set, I made sure that the training and validation set were split to have the same distribution proportions. So you'll see the figure on the right now that even though the counts for the validation set are much less because it's only 30%, the proportion for each class is the same as in the entire training data set. And what this visualization told me is that there probably should be some technique used to handle this class imbalance. So one of the things that I found when I was researching was class weighting. So I'll be using class weighting practices to handle the imbalances. Class weighting is when you assign a weight for each class so that the higher weighted classes will be the ones that the model focuses on learning more pretty much. So the higher weighted classes will be the undersampled classes so that there's more error for in classifications when the model incorrectly classifies them. So they focus more on learning those undersampled classes, and that compensates for the less samples they have for that class. Another visualization I used is the training loss graph. So during the training, the model attempts to minimize the loss function during training. The loss is pretty much the difference between the predicted probability and the actual class. So it's a measure of error between the predictions versus the actual observations, specifically the predicted probability versus the actual observations. The loss should be decreasing during the training. It should, during the first batches pass through, it should be at its highest, and then towards the end, it should be at its lowest point because the model is minimizing the loss function. So if the model is successfully doing that, it's successfully learning the data, the function should be decreasing. And if you see the graph begin to plateau, this one isn't plateauing, but if the graph plateaus towards the end, that means um, that the model might be getting overfit because it's not learning much more. And that's a good time to stop the training. So it can also be used to show when the model is going to start overfitting. Now for best visualization, updating the model weights. So I'm using pre-trained models in this analysis, meaning that the model architecture was already developed and the models were already trained on previous data. Um, so the previous data that the model was trained on, when the model was trained on that data, it already learns the weights for that data. And I'll continue talking about the pre-training process later, but when you import the model, you can either use the weights that it learned during that pre-training, or you can import those same weights, but you can update them during your training. So if the model is only using the weights for pre-training and not updating them, the weights are frozen. And if you're updating them during your training, they're unfrozen. So I tested both. You'll see on the left when I use the frozen weights, I actually expected this to train faster since it's not updating and to maybe even be more accurate because the pre-training involves training on millions of images, a lot more than in this data set. But it actually shows that when the weights were updated from this training, the performance was much better when the weights were updated when they were unfrozen. Um, so it just shows that updating the weights tailors the model much more to this classification problem. And for all testing done, the weights remained unfrozen to specifically tailor the model to this image classification task. And for the model description, so each model again was pre-trained on the ImageNet data set that is the largest data set online of images. It's pretty much the standard to train and test image classification models. It contains 14 million images. Um, all these models are built and trained on that. And then all you do is import the pre-trained model and you adjust the final layers of the model to output the correct classification classes that you're using in your project. So I just adjust the final layer to output eight classes that we're using in this project. And this is supposed to be a lot more computationally efficient. It allows you access to state-of-the-art and very complex models as well. So these pre-trained models, a lot of them have 50 or even 100 different layers, which if you were developing that on yourself, that would take a long time to train and test. So the training and testing time is much, much smaller when you use these pre-trained models. So the first model architecture that I'm training is the ResNet and ResNext model architecture. It was developed by Microsoft in 2015. It's a convolutional neural network type. And the main differentiator about this, big innovation, was that it used residual connections in the layers. So what that did is there's connections in the neural network between layers that are non-sequential. And this eliminates the vanishing gradient problem because as data is pushed through as the gradient is propagated through the network, it begins to get too small to accurately update the weights. So when you add these connections that kind of skip layers, it allows the gradient not to diminish as much and the network can increase depth without sacrificing much performance. Next was the EfficientNet V1 and V2 models. This is slightly newer, developed in 2019, and V2 was developed, I believe, in 2021. But the model scales uniformly or dynamically as the image size increases. So as the original image is actually increases in size during the training, and it's believed that larger resolution leads to better model accuracy. And this increases computational efficiency and trains in a fraction of the time as the previous CNN architectures. The vision transformer models is not a convolutional neural network like the other two, but it's a transformer model. Transformers were developed by Google in 2017. The attention mechanism in the model detects ways that sequential data elements impact each other. And this was kind of groundbreaking because it's originally developed for NLP solutions. It's what powers ChatGPT, but it's been groundbreaking in NLP, and it's been adjusted to work in the computer vision space. So it's been competitive in the computer vision space, and it's the capabilities of it are also tested in this analysis. The model performance. So for each model test run, you will see in the image right here. So the models with the highest validation accuracy were the ResNext 50 model and the EfficientNet V2 model. So ResNext is the more advanced version of ResNet, and EfficientNet V2 is obviously an upgrade from EfficientNet V1. So those had the highest accuracy. You can see the EfficientNet V2 had very low training loss of 0.36. And the EfficientNet, since it's more efficient, I was able to run more epochs of data through it and use a larger image size, and without the training time taking much longer. It still took less time to train than one epoch for the ResNext. And you'll see all the adjustments when I use class weighting. Surprisingly, it actually decreased the performance of the model. And I believe that's because when I actually looked at the classifications for the minority classes, both models were able to effectively classify the minority classes. So there was enough samples for them to learn the information for hogs and rodents. So the class weighting might have just deterred the model more from classifying the majority classes, resulting in worse performance. So it was not a practice that I thought that it looks like it wasn't a practice that was actually necessary because the model had enough information to identify the minority classes. And vision transformers were extremely underfit. You can see that they were actually the worst performing, which a bit surprising, but looks like they just needed a lot more data to effectively learn what the other CNN models used. Only when I started using 20 epochs of data, which was 20 times what I needed for the other models, they performed fine with one. Then it started posting respectable accuracies around 62 and 65. So when I'm looking at the championship models, you'll see the two confusion matrices for the ResNex 50 and the Efficient V2, the top scoring models. The ResNex posted a higher accuracy by like zero point zero 0.06, and it classified blank images better and hogs better. You'll see on the left that it correctly classified 195 blank images to efficient nets 142. So if you were looking for a model that you really wanted to focus on classifying blank images, which I could see as a big use case for that, is there an animal there or not? You might go with the ResNex 50 model, but I actually believe the Fishnet V2 model was the championship model because posted very respectable. I mean, it posted pretty much the same accuracy, and it trains in a fraction of the time. I wanted to say it trained in like maybe for one epoch, like a tenth of the time, maybe something like that, depending on the GPU usage. Um, and it posted very similar accuracy, and it still classified 4 out of the 8 classes better than the ResNex 50 model. So that could be the championship model as well. And that was my choice for the championship model. So the log loss for the KPI review, I set a log loss of 0.53 for the validation set. Um, the lowest training loss was 0.36 for the efficient FV2 model. Most models had between 0.8 and 1.2. The actual log loss will be calculated by driven data after the test label submission. Accuracy KPI was set at 80%. You'll see that 2 models hit 77%. But it's notable that I was only using 50% of the training data because of computational resource limits. I mean, it took the ResNex model like an hour and a half to train and 30 minutes to test, so it's I was very limited by resources. So additional training data, parameter tuning, and model optimization should move validation accuracy above the target. Um, it should move that about 88% to above 80%. I didn't put it here, but I actually ran the efficient at V2 with all the data, and it took about like 3 or 4 hours, and the accuracy went to 88% for one trial, just one trial run though. So I do think, even though the reported accuracy, I could only honestly report like 77%, I do believe I hit that target. And operational efficiency, um, the ResNet models took an hour and a half to train, 5.5 hours to validate. EfficientX took even less than half an hour to train, about half an hour to train at most for one epoch, and just a couple minutes to validate. So the model training testing is exponentially faster than manual image labeling and manual image labeling. So manual image labeling. So the operational efficiency KPI was definitely hit. It's definitely much more efficient than doing it manually by hand. So for recommendations to improve it, I would add more data augmentation. So you can do things like flipping each image, rotating each image, and this just gives you more samples for valid data, and it'll teach the model to learn to classify the animals like in different positions. So like just flipping the image horizontally, vertically, or rotating it. You generate more samples for your test set, just the original image and the flipped or rotated image. And grayscaling, which is just taking the image and making it gray. A lot of the images at night were gray, black and white already, so makes sense to get them all on the same scale. You should also add more resources. Make sure your resources are capable. I would suggest even using a TPU because it takes an hour and a half to train on the GPU sometimes. And if possible, optimize each model separately before comparison. What I had to do is I had to pretty much test each model with the same parameters because they took so long to train. I found parameters that worked pretty well and then applied them for more models. But what you actually should do if you have the time and resources is optimize each model separately to its potential and then compare each fully optimized model to each other. I was pretty much comparing like partially optimized models to each other. And lessons learned, that image classification very, very expensive and wouldn't have been possible without a GPU and expanded memory using the resources from Google Colab Pro. Had to upgrade. Um, Pre-trained models are complex and easy to implement. It's called transfer learning, and it works because the pre-training allows the models to already learn general image classification features. So these features that it learns to classify images are actually general. You can apply them for different classification tests, so that's why it allows you can transfer the learning of the pre-training to use in R situation, and the training time goes down by a lot, and it makes it a lot usable and accessible to complex model architecture. The efficient Net v2 is one of the most state-of-the-art model architectures with fast training and great performance, and is much more scalable than any other model that I tested. And vision transformers have much differences than convolutional neural network models. I believe to make it effective, I would have to use much more data and specialize the parameter tuning just for that model. Also, the championship model selection for multi-class classification depends on the specific use case. I picked the efficient V2 model, but there's a couple cases for the ResNext 50 model as well if you're more concerned about blank images or one of those specific image classes. So thank you guys for my presentation. Hope you learned a lot. Hope you enjoyed it. And that concludes it. Let me know if you guys have any questions.